The weathering of granite and other rocks may result in the formation of a residual regolith of clay, rock fragments, and quartz grains. Another important result of weathering is the removal of some of the rock in aqueous solution. Matter in solution cannot be seen and does not accumulate with regolith, but is carried away from the site of weathering in streams. Other geologic processes which affect these two types of weathered material will be studied using the flowchart in your laboratory manual. As long as the solid products of weathering remain at the site where they were formed, they constitute residual regolith. In time, however, these materials may slide downhill into a stream, a lake, or the sea. Some are moved by glacier ice or wind. Thus, weathered rock is redistributed by the processes of erosion and transportation. To determine how residual regolith is redistributed after it slips into a lake, some controlled observations can be made in the laboratory. Note the results of these observations in the table in your laboratory manual as shown in this example. A sample of regolith can be separated into fractions of uniform particle diameter. This is done by passing it through a series of sieves that have progressively smaller openings. The material retained on the coarsest sieve is composed of particles whose diameter is greater than 2,000 microns. This is fraction 1, and material this size is called gravel. The material retained on the next sieve in the series passed through the 2,000 micron screen, but was trapped on one whose openings are 62.5 microns in diameter. This material is sand. Fraction 3 passed through the 62.5 micron sieve, but was trapped on one with openings 4 microns in diameter. It is silt. Fraction 4 passed through all sieves, so it is composed of particles that are smaller in diameter than 4 microns. Examination under high magnification reveals that this material is almost entirely clay. Using this glass cylinder to represent a body of standing water, such as a lake, the settling rates of the 4 fractions can be studied. First, the depth of the water must be known, which in this case is 50 centimeters. The length of time it takes for each fraction to sink to the bottom must also be determined. Record the times in the appropriate space in column 4 of your table. First, fraction 1 is poured into the column. Gravel takes 2 seconds to settle a distance of 50 centimeters. Record this value. Sand-sized material is timed. Silt-sized material requires 72 seconds to settle 50 centimeters. Even after a good deal of time, not all the clay-sized material has settled. Some will remain suspended for hours. Mechanical disintegration of rock in the early phases of weathering might form fragments like these. Observe that the dark-colored fragments are harder than the lighter ones. When fragments like these slide into a stream, they are rubbed against one another by the action of the current as it moves them downstream. To study the effects of abrasion, we must speed up the process. This can be done by shaking some of the fragments in a bottle of clear water. After half an hour of shaking, the water is poured off. Notice that it is milky, with fine material suspended in it. The fine material will ultimately settle to form a thin layer of sediment in still water. Here, several hours are condensed into a few seconds by time-lapse photography. The sedimentation process taking place in the dish on the left is also taking place in the lake on the right. Now let us examine the rock fragments. The harder fragments show little obvious wear. But the softer material has had its corners worn off, and the average size of the fragments is smaller. Cross-stratification is an important structure of sedimentary rocks. To illustrate the significance of cross-stratification, a cross-stratified deposit can be produced in the laboratory. This glass box filled with water represents a lake. The clear trough represents the channel of a stream flowing into the lake. When sand is poured into the stream, it is carried to the lake bottom and deposited there. Speeding up the action photographically and varying the color of the sand, a distinct pattern develops. Note the S-shape of the individual beds. Note also that as the lake is filled, the cross strata are cut off or truncated near the stream inlet. The position of the stream mouth is changed, and the water level in the lake is raised. A new deposit is now built on top of the old one. This deposit has the same structure as the first one, but the difference in current direction is shown by the opposed direction of the cross strata. Cross-stratified deposits indicate the direction the current was flowing while the sediment accumulated. In addition, the position of truncated cross strata show which surface of the bed was originally on top.